Representing enthalpy practice questions. In the previous video, we looked at representing enthalpy, and we did it in 4 different methods, 4 different ways. So please look at that video before you continue with this video, because this video is just a reiteration and practicing using application what we learned in the last video to solve some problems. And we're going to be doing it together, followed by some practice sample questions. Last ended off with this thermochemical equation, and again it's thermochem, not a balanced chemical equation, because even though this is a balanced chemical equation, it is also including the enthalpy change. And we did this for the cellular respiration, and this here is the thermochem equation. We're going to do the same thing but the reverse for photosynthesis, and we're going to do 4 different methodologies for photosynthesis. So let's start off with the first thermochem equation. We're just going to write down exactly what we have here, but it's going to look a little bit different because that value at the end over here needs to be on this side. So I'm going to add it over here. And the reason why we do that is because it is endothermic. It's taking in energy. When the plants take in the light, it is taking that energy, and that potential energy is now increasing. So it's taking it in. So it needs to be on this side. Well, that's the first methodology. But our second methodology, you just need to copy paste what we have here. And rather than having it on either side, the reactant side or the product side, we're just putting a delta H at the very end of the equation, and we're just going to write the symbol, so the positive or the negative, following suit of what we had. So in this case, it was a positive value, so we're just going to put positive over here. That's it. So that's the second methodology. Now let's look at the third methodology. And the third methodology is the delta H. And it's going to be a little not symbol here because it's going to be the standard molar enthalpy, and the standard molar enthalpy for photosynthesis is going to be this value over here. And again, we follow suit with the symbol. So it's positive, so we're just writing positive 2802.7 kilojoules, but do not forget to put per mole of that glucose. The glucose is the one that is reacting with oxygen over there. So that is the third methodology. And then the fourth methodology was using a potential energy diagram. So again, potential energy measured in kilojoules. Let's have it going up there, and then we have reaction progress down here. Okay, let's start with our reactants. So I'll just label it as R for reactants. So these here are the reactants, and it's going to take in that energy. It's going to hit an activation energy, that threshold over here, and once it crosses that line, okay, it's going to undergo the reaction. And now we have here for P, the products. All right, and you can see the difference between the reactants here and the products over here. The difference there is going to be the delta H, and the delta H is going to be represented as a positive value because we have increased the potential energy. So this 2802.7 kilojoules, as you can see, it is a positive value. It's endothermic. The potential energy has increased from where it was in the reactants. So this here is the fourth methodology. All right, let's look at our first question over here. It says a compound such as calcium carbonate can decompose by absorbing energy. This reaction can be written as calcium carbonate yields calcium oxide and carbon dioxide. Identify which has the greater potential energy, the reactants or the products. Well, the best way to be doing this kind of question is by looking at a potential energy diagram. So again, we have a reaction progress here. We have our potential energy in kilojoules going up this way, and we have our CaO CO2, so that's right over here, the reactants, and it's going to be taking in energy. So this is endothermic. So it's taking in that energy, and now the products are going to be higher. The potential energy for the products are going to be higher than the potential energy than it was in the reactants. So this here are the products, right? The calcium oxide and the CO2. So you just find the difference between the two. And as you can see, the difference here is going to be positive. So which one has a greater potential energy? Definitely the products, because look at it on the scale. Products are all the way up here. reactants are all the way down here. If you look at it from the y-axis, the potential energy increase is going up, so of course the product is going to be higher. So the answer is going to be the products. B, is the enthalpy of the system increasing or decreasing? Well, it's obviously going to be increasing. As you can see here, the value is going to be positive, so it's going to be increasing. Next, is the reaction endothermic or exothermic? It is absolutely endothermic because we see the energy on the reactant side. If it's on the reactant side, it's taking in energy. Last but not least, is the enthalpy change positive or negative? It's absolutely going to be positive because, again, the difference between the product potential energy and the reactant potential energy is a positive value, because you just do this, subtract this, is going to give you a positive value. Let's look at this new question here. So we have the standard mole enthalpy of combustion for hydrogen to produce water, and its vapor, is negative 241.8 kilojoules per mole. The standard molar enthalpy for the decomposition for water vapor is this many kilojoules per mole. You can see how that they're the same value, however they're in opposite symbols. So we're going to write both chemical equations as thermochemical equations. Let's first try out with the first one. As you can see, it is to produce H2O. So let's write that out here. It's going to produce H2O, and it's going to be gaseous here. But what are our reactants? Well, we only have hydrogen, so we're just going to write hydrogen. And again, it's diatomic, so I'm going to put a small 2 down here. So I'm going to put gaseous. And it says combustion. The hint there is that it's combustion, so it has to add oxygen, or else it won't work out. Again, I'm putting a 2 down here as well because it is a diatomic molecule. And then I'm going to be putting our gaseous state over here. Now, as you can tell, it's not balanced, so let's just quickly balance this out so that it is appropriate. Again, pause the video if you wish. Try balancing it on your own. All right, hopefully you balanced it. So we got a 2 over here and a 2 over here. That's pretty much it. Now that that's done, we need to look at the thermochemical equation. Well, this here is per mole of H2O, but we don't have per mole of H2O right now. We have 2 moles of H2O. Okay, per mole is 1 mole. We actually have 2. So rather than negative 241.8, we need to multiply it by 2. So it's going to be double because we have a coefficient of 2 here. We have to double it. And again, it's a negative value, so it needs to be on the product side. So I'm just going to add it over here. And the value, again, it's going to be negative 241.8 times 2. So that will be negative 483.6. So I'm going to put negative 483.6 kilojoules. Again, I'm saying negative, but I only need to write positive here because it's on the product side, so it's going to be seen as negative anyway. So that's it. So that is the thermochem equation with a delta H value for the first one. Now we're going to be doing it for the second one, the standard molar enthalpy for the decomposition of water vapor. So let's have water vapor here now. And again, it's going to be producing something. It's going to be decomposing. So what is it going to decompose into? Well, we have the reactants here. So of course, the same reactants are going to be in the products here. And again, this has hydrogen, this has oxygen. So it obviously has to be hydrogen. And it obviously has to be oxygen. Again, these are diatomic, so let's not forget those. But the gaseous states for these. And we're done. We just have to look at our 241.8 kilojoules per mole. Well, again, we have to see that these are balanced out accordingly. And if this here is our value, 241.8 kilojoules per mole of H2O, but we don't have per mole of H2O, we have 2 moles of H2O. So we're going to multiply this value by 2. So it's going to be 483.6. But rather than it being on this side, it's going to be on this side now. As such. Now, we just have to answer the question. For B, how does the enthalpy change for the combustion of hydrogen compare with the enthalpy change for the simple decomposition of water vapor? Well, this first one over here, so I'm just going to answer B up here because we still have some space. It's that H2, so this one over here, right, the H2 is going to be exothermic. So the H2 is exothermic. This one over here for the H2O in question, it is endothermic. So the H2O is going to be endothermic. However, to finish off this question, how do they compare? They're the same value. right? As you can see, 483.6 for the whole thing and 43.6 for the whole thing. This is just the negative value, is exo, and this here is the positive value, it's endo. They're the same value, but with opposite sign. All right? And again, if we look at it per mole, it's negative 241.8 kilojoules per mole of hydrogen and 241.8 kilojoules per mole of the H2O vapor. So if you want to look at it not in terms of 483.6 and 43.6, you can just bring it down to its base form, which is 241.8. And as you can see here, this is a negative 241.8, whereas this here is a positive 241.8. That's what I'm iterating here. It's the same value, the same number, 241.8, but this one here is a negative and this one here is a positive. All right, next question. Translate each of the molar enthalpies given below into a balanced thermochemical equation, including delta H. Again, if we have a balanced chemical equation and there's also delta H involved in there, that means the whole thing is actually going to be called a balanced thermochemical equation. This was methodology number 1. Hopefully you remember that. Okay, let's continue. The enthalpy change for the reaction in which solid magnesium hydroxide is formed. It's going to be formed. So I'm just going to put MgOH. I'm going to write down our givens as we go along in the question. MgOH2, right? We're going to cross over that charge over here. And again, it says solid, so I'm just going to add a solid over here. Okay, from its elements at SATP. Well, before we look at SATP, from its elements, what elements are going to be there? Well, obviously there has to be a magnesium. Okay, well, what else are there going to be? Is it going to be adding with H2O, for example? The problem is when we use H2O and this is going to dissociate into its respective cations and anions, it's not going to be possible because Mg itself is an element. It's smallest form anyway, so it's not going to be H2O. It's impossible. It's not going to dissociate. So rather than figuring it out that way, we can just honestly just put H and we can just put O, because that's what we need from this side, right? O and H. We need an O and H on this side for it to make sense. Now O is diatomic and H is going to be diatomic, so we're good. And we're just going to put our states. Obviously this is going to be gaseous, magnesium obviously solid, and H2 obviously gaseous again. So we're just going to have to balance it out. Looks pretty balanced to me on either side, so we don't have to continue that. And then we're just going to have to figure out our SATP is at negative 925 kilojoules per mole. Again, it's exothermic. It's negative that value. So this negative here means it needs to be on the product side. So I'm just going to put plus 925 kilojoules. That's it for that question. Let's do B. The standard molar enthalpy of combustion for pentane is C5H12. I'm just going to write down C5H12. Now, what are we going to be doing? Well, we have to do a combustion reaction, so it obviously has to add with oxygen. And then it's going to be creating CO2. Again, we're just going to assume this is complete combustion. As such, now we're good. Now you just have to make sure that you balance it out appropriately. So please pause the video and try to balance it. All right, hopefully balanced it out appropriately. There's going to be an 8 coefficient over there. There's going to be a 6 coefficient over here. And there's going to be a 5 coefficient over here. Now, it says negative 2018. It is exothermic. It is a negative symbol. So we have to add negative 2018 over here. Again, it's on the product sides. Hence, we have the positive. Similarly up here. Now let's look at C. The standard molar enthalpy of simple decomposition. So delta H not standard. Decomposition for nickel 2 oxide to its elements is 240 kilojoules per mole. Well, let's write out what we have here, our nickel 2 oxide. So we have nickel 2 oxide here, and we're just going to make it a solid here. And then it's going to break out and decompose into its respective products. Well, of course, there has to be nickel on one side, and then it has to be oxygen as well on that side. And then this one here is diatomic, so I'll just put a small 2. We obviously have to balance this out. Please pause the video, give it a try to balance it. All right, you should have figured it out that you have to put a 2 in front of there and another 2 in front of here. So now we're good. Again, this should be solid, this should be gaseous. And then what we're going to be doing now is putting in our 240 kilojoules per mole. Well, here's the problem. This kilojoules per mole is in regards to the nickel 2 oxide in question. The problem is that is per mole of this one. We've figured out after we've balanced this equation that there is 2 moles of that. So rather than 240, we need to multiply this value by 2 because we have 2 moles of this right now. So we're going to have to figure it out and do our little calculation. So you end up just getting 480. So we're going to be adding 480 where on the reactant side or on the product side? It has to be on the reactant side because it is a positive value. It's plus 240, not negative 240. So I'm just going to rewrite this. I'm just going to squeeze it in there. And this one here is going to be 480 kilojoules. That's about it. We're done. Right, so here are the green questions of the day. So this here is the first question. This here is the second question. This here is the third question. Please give it a try on your own, and then I'm going to be giving you the answers shortly. This here is the answer for the first question. This here is the answer for the second question, and this here is the answer for the third question.